Okay, good morning, everyone, and welcome back to day 4 of String Math. Our first speaker here is Mirjam from UPenn and also at CERN this year. So she'll tell us about the geometry of higher form group structures in string.
Okay. Well, thank you to the organizers for the invitation to this wonderful conference and to running it so smoothly and so well. So what I would like to talk about is about some recent work where we try to use geometry and actually topology of a string theory to determine the structure of higher form symmetries in resulting quantum field theory. So the main motivation for this work is to study string theory or M theory on special holonomy spaces and getting thus in lower dimension an effective field theory. When such special holonomy spaces are non-compact, we employ actually corresponding geometric engineering of this compactification to determine features of the resulting supersymmetric quantum field theories. In this program, one builds the dictionary between, say, operators and symmetries in the resulting SQFT and the features of geometry, topology of this non-compact space. So in this talk, I'm going to focus on higher form global symmetries, which are associated with flavor branes that extend to the boundary of these non-compact spaces and relate the features of this higher form symmetry actually to singular topology on the boundary of these non-compact spaces. When the space becomes compact, then our resulting quantum field theory necessarily also includes quantum gravity, as this is part of string theory. In this context, higher form symmetries cannot be global anymore. They can either be gauged or broken. And to identify actually physical consistency conditions under which we can have a really non-anomalous proper gauged higher form symmetry is one direction in many prongs of swampland program. So I will focus, of course, on this aspect, as I was already advertising. And this is a work actually that has a really very active community. First of all, the study of higher form symmetries in supersymmetric quantum field theory is just booming, and it was initiated in earlier work by Gayotto et al. We have heard at this conference talks by Lakshya Bardwai and also by Dan Fried. But my focus is on geometric engineering. And so I would be talking about the origin of higher form symmetries on non-compact special holonomy spaces. And this is again also very big field as far as higher form symmetries go, initiated in earlier work by Del Zotto et al. And then you can see a big lots of dots, lots of authors involved in that. My work, my presentation here will build on the work that quantify geometrically the origin of defect groups and their association with higher form symmetries in such geometries. And then, of course, focus on the work where we are using the topology of boundary spaces to determine them. And I should point out there was also at the same time a related work by Del Zotto et al. As well. This work actually was also had some talks at this conference, in particular Muyang Liu and Paul Ullman presenting some of the aspects in a parallel session. So again, the goal is to identify the origin of higher form symmetries for M theory. I'll choose M theory as prototype and choose non-compact special holonomy spaces in diverse dimensions. Okay. The punchline is actually that this higher form structure, in particular, 0 forum, 1 forum, and 2 group symmetry structures can be obtained from singular boundary geometry by studying singular homologies there, exploiting their cutting and gluing of the singular boundary geometries. So it's all from the singular boundaries. The primary examples that I'm going to choose would be on elliptically fibered Calabi-Yau M-folds, in part because they have also interesting duality to F theory. And it's building actually on bigger program that we developed also by studying non-compact orbifolds in diverse dimensions, as well as local G2 holonomy spaces. At the end, if time permits, I will also make a few statements about compact examples, in particular connections that we draw there from dual F theory compactification. Any questions? Okay, so again, as advertised, this is work primarily based on this recent paper together with Jonathan Heckman, Max Hubner, who is a postdoctoral fellow at Penn, and Ethan Torres, who is a student there, where actually we quantify the things that I have said so far just in punchlines for non-compact examples, but we are also working hard on addressing those issues in compact constructions, which we hope to appear very soon. Actually, this work is not unrelated to another program that I've been pursuing, primarily in collaboration with Marcus Dirigal, who was at Penn but is now at LMU, Ling Lin, who was at Penn and is now at CERN, soon to be at Oxford, and Hao Zhang, a student at Penn. Namely, there we were focusing on the features of, again, topology, higher form symmetries, in primarily trying to address that in the compact A-dimensional examples from string theory, and draw also physical constraints on such global topology by, again, exploring higher form symmetries. And some of the work here that I'm going to present will employ the results where we studied that, again, higher form symmetries on Calabi-Yau fourfolds. Apologies. On elliptically fibered Calabi-Yau twofold down to 8 dimensions. Okay, so the rest of my talk will involve some general introduction about the topic of higher form symmetries. Then we'll continue its connection to defect groups, and of course I'll highlight the example of how we determine topology of flavor symmetry from this geometric features. I will say a few things on the origin of 2 groups, again also from the singular homology of boundary geometry. And if time permits, I'll say a few things about compact, primarily elliptic examples, their connection to F theory, and actually to arithmetic structure of the elliptic curves associated with the Mordell Weil group, and how this may be related to the fate of higher form symmetries there, and some concluding remarks. Okay. So when studying the defect group of M theory on non-compact spaces, we are focusing on p-dimensional operators in resulting lower dimensional supersymmetric quantum field theory. So we want to identify the origin of p-dimensional operators in resulting field theory by studying M2 branes in M theory and M5 branes wrapping certain cycles in the non-compact space. So there's cycles that M2 brane and 5 brane wrap live on relative cycles because the space is non-compact. And in particular for M2 brane, the p-dimensional operators are associated with the relative cycles in D minus 3 minus p homology of this relative cycles that have to extend now to the boundary. And for that reason, we have to mod out this relative homology also by the cycles that are associated with the compact space, that are compact by themselves. Okay. It can be shown that such relative homology of such cycles, relative cycles that extend to the boundary, can be expressed in 1 degree lower homology of the corresponding 1 degree lower homology in the corresponding boundary of this non-compact space. And in particular, those should be only cycles that when we include the boundary inside the full space, they become trivial, so they don't extend in the bulk. Okay. So in particular, this relationship that was derived in those papers, okay, tells us about the nature of p-dimensional operators for M2 brane, so associated with the electric operators there, and reading them off from the boundary homology in 3 minus p minus 1 degree. And similar expression we get also for p-dimensional operators of the corresponding M5 brane wrapping this non-compact relative cycles that extend to the boundary. And again, expressed in terms of the 1 degree lower homology of the corresponding boundary. So in particular, the defect pairing that we are dealing with in the resulting field theory is geometrically related in 1-to-1 correspondence to the corresponding linking pairing of the cycles in the boundary homology. So let me show you an example of identifying such a defect group by looking at M theory on non-compact K3 and choosing that for elliptically fibered K3, where the base is just complex plane. So the fibration is in general singular. And let's focus on the case when we have a Kodaira type singularity at point Z in the base associated with a specific monodromy M. Okay. Now, as we go to the boundary of this non-compact space, the boundary is actually fibered by a circle. Specifically, we can determine the degree n homologies in this boundary space, in this case, by using the action of the specific monodromy associated with the singular fiber, okay, that acts in homology of degree n. This calculation will allow us to determine, in principle, H1 now, that is in the boundary that has to be associated with particular defect. So in particular, my focus is on one-form symmetries. So this would be an electric one. So this would be M2 brane wrapping in the bulk relative 2 cycles, torsional 2 cycles that extend to the boundary. In the elliptic fibration, we can describe this via Kodaira fiber that goes, that blows up toward the asymptotic boundary. And the sequence allows us to determine that, which is H1 in the boundary homology, and that gives us the actual result that this is co-kernel of this monodromy, torsional part of the kernel of this monodromy minus identity. And this group of this defect I'm going to refer to as Kodaira thimbles. So we have now the defect group associated with this Kodaira thimbles, and this construction engineers now for us specifically 7-dimensional super Yang-Mills theory with the gauge algebra associated with this monodromy G sub f, the type of the generation of Kodaira fiber, and the specific defect group of Kodaira thimbles. So these Kodaira thimbles actually have self-linking intersections. Okay, so they are non-zero. And also this implies that these elements of D1 defect group of M2 brane and D4 defect group are typically mutually non-local. I will choose from now on really only the mutually local examples in the electric part, and that we would refer to as electric polarization associated with line defects of M2 brane. Now, again, outcome of this analysis is that, again, we are talking about gauge group here in this case that is simply connected, associated with the generation of Kodaira fiber. The resulting gauge symmetry actually has the gauge group whose center we can now determine by identifying now those line operators that are acted on by one form symmetry action. This is actually, this one form symmetry is actually Pontryagin dual description of the corresponding line operators. And that would then in turn determine, fix the really topology of the corresponding gauge group, not just the Lie algebra. Okay, so now let's turn to higher structure in dimensions bigger than 4. So let's do special holonomy spaces in dimensions of dimension 6 or higher, and this will lead us to more involved structure of new phenomena associated with the higher form symmetries. Okay, so let me now first turn again how we geometrize topology of this flavor group. Okay, so the flavor group in general on this non-compact space, now possibly in higher dimensions, are associated with AD loci on the boundary of this non-compact symmetry, non-compact special holonomy space. Okay, and we can identify from the type of the singularity, the naive flavor group, okay, associated basically with the Lie algebra that we identify. I will from now on really deal only with the AD type loci in the boundary, and so this would be then in this case the naive gauge symmetry of the flavor branes. Okay, now we have to identify the corresponding flavor lines, namely line operators or one form symmetries by Poincare dualities, which we then fix topology of this flavor group to the real group GF. Okay, and again, as advertised, I'm going to do that from singular boundary topology. Okay, so in this context, right, of describing the flavor branes on the boundary of non-compact geometry, we are dealing with non-compact space, and on the boundary, as I am emphasizing, we have singularities, AD loci, that sit on this boundary. Now, the way we want to handle the origin of these higher form symmetries and the real global structure topology of the brane gauge group, we are going to define the smooth boundary by excising the singularity of ADE loci. But also we are going to go a little bit away from the singularities and introduce this tubular region that excises the singularity. So in particular, the intersection of this tubular region with a smooth boundary now turns out to be the union of this ADE loci together with the orbifolds, a singularity of S3. So that's a general geometrical picture. And we can now argue that this naive center symmetry, which is the center of this original Lie algebra, can be identified as the torsional first homology of this intersection of tubular region with the free, with the smooth boundary, and is just associated with the corresponding centers. But that's not what we want. We actually want to know what is the genuine flavor center symmetry. And for that reason, we have to now deal with this gluing, cutting and gluing of the singularities and identify homologies in the corresponding of this corresponding singular spaces. So let's, for that, it turns out that actually mathematicians have done work for us. There is actually Meyer-Viatori sequence in homology of singular boundaries that we describe now, as I said, in terms of this, the smooth one and this tubular excision itself. And this Viatori sequence actually allows us now to define short exact sequence in these geometries through which we identify the corresponding operators or form symmetries. Okay. So in particular, we obtain for this particular boundary study this exact short sequence, okay, that involves the one form that involves first homology of the corresponding boundary. This would be associated through Poincaré duality to one form symmetry or line operators. And then the corresponding Meyer-Viatori sequence then goes over by separating the singular space into homologies of its pieces. And we end up with the kernel of the map between the this intersection of tubular excision and the regular part, which I already argued is the naive flavor symmetry. And then the map onto this homology is associated with what I would refer to naive one form symmetry and eventually the real one form symmetry. But the flavor center is in the kernel of this map. And so it's this flavor center that will identify for us the true center of the gauge symmetry, namely as a kernel of the map of the naive flavor symmetry onto naive one form symmetry. There are some other relations to forms. In any case, in this calculation, now for specific example, we were motivated by studying orbifold homology of this singular boundary, and actually were able to argue through previous work of mathematicians that actually first homology of this regular space is related to orbifold homology of the full singular space itself. Just a technical detail. In any case, with this understanding of the real center of the flavor symmetry. We can demonstrate that now again on a particular example. So in this case, it would be elliptically fibered threefold. So we are now in the non-compact space where we choose the base to be non-compact, C2, and choose specifically the degeneration of discriminate loci in this elliptic fibration to be of the type of one locus, discriminant locus that extends now to the boundary in the base, and the other one perpendicular one. Okay, and now we are in one dimension higher. So boundary manifold in this case is actually elliptic fibration over S3. But in particular, what we want to focus now is on this discriminant locus that would involve on the boundary linking circles associated with phi L and phi R part. And so this is basically now talking about linking circles, very similar like in the previous case, but now we just have two of them, and we have to carefully work out the corresponding first homology in the boundary associated with the corresponding monodromies acting on degree n homologies. In our case, we want to focus on H1, both for the SL1, for the linking circle with one discriminant locus, and then the second one. And the corresponding results actually gives us the torsion homology of this regular space to be related to the corresponding monodromies. And through the Myers-Vietoris sequence, then we get the genuine corresponding global center of the symmetry. And in this case, this is the example where we are dealing with two, for example, SUN loci, and then obtain now the global form of the flavor symmetry by looking at the largest common denominator of N and M, and in general is really the diagonal center of GL and GR. So those are, of course, one can generalize that also to more general basis in elliptic fibration. And that would involve a little bit more detailed studies of the corresponding torsional homology there. That would involve also the homologies in the base. I don't have time to go into that, but this allows us to determine the whole global flavor structure for a number of other examples. Now, we studied also other examples of non-compact geometry. In particular, we looked at all the six-dimensional orbifolds. And also we looked at the examples of other examples of Calabi-Yau threefolds, and dealing also with interpretation of R-form symmetries in local G2 holonomy spaces. But I really don't have time for that, and would like to now turn to the next stage to uncover even richer structure, not just the center, the topology of flavor group, and that involves really the larger structure of so-called two groups. And when can such a larger structure of two groups really appear in the study of the boundary homologies that I was outlining here? So for existence of two groups, we are dealing with two particular short exact sequences that involve the center of the brains of the groups, naive and the real center, and also another one that is associated with the corresponding line operators, okay, together with extension problem of Postnikov class that specifies then finally what the global structure is. And so let me just point out again the building blocks here. in this short exact sequences. So we are dealing with the center flavor symmetry, the one that I already determined in examples or studied via Meyer-Vietoris. Then there is naive one, also the way we address that already. And then as I'm advertising, there is the real line operators modulo, those that are screening by local operators, along with the naive operators that are screened by local, modulo screening by local operators that transform under the representation of the real center of the flavor group. And so there is another building block here, C, that is associated with line operators that sit now in the kernel of this map of naive line operators into the real line operators of the theory. Okay, and of course, this whole story can be also written in the Pontryagin dual structures, where line operators are interchanged and with one forms. We can actually do that for the second line sequence and reverse the arrows and get the structure of the exact sequences, namely the first one again signifies the zero form, namely the discrete part of zero form symmetry. The second one is now associated with the one form symmetry together with the Postnikov class. And this is basically the key features we were playing already. But what is crucial now is that it's sufficient that in the second sequence, if it doesn't split trivially, namely if the naive one form symmetry is not direct product of this kernel of the map and the real one form symmetry, if namely this is non-trivial one, then we do have a non-trivial group structure. Namely, there is an interplay of zero form and line operators that local operators and line operators actually are intertwined in non-trivial way, forming a two-group structure. And typically what we actually do, we now also collapse these two exact sequences by removing C and get what one would like to refer to as a non-trivial two-group structure associated with collapse of those two sequences. Now, how does this structure that I describe in the abstract refer actually to Meyer-Vietoris? And again, from these physical arguments, we have derived parallel homology sequences in this boundary homology by using physical interpretation of these terms and obtain this short exact sequence and that short exact sequence, and collapsing them, that would be precisely the exact sequence I started with, okay, and would be a two-group sequence. So in particular, this is precisely the two-group sequences I was talking about by interpreting each of the terms in this homology of the singular boundary to the corresponding zero form and one form symmetries. And specifically, if this term here is not the sum of those two, then we are really having genuine two-group structure. And so namely, if the bottom sequence doesn't split, we gain precisely in one-to-one correspondence get the relationship of mixing of zero form and one form symmetry, flavor symmetries in a two-group context. Okay, so with this sort of overview of our topological geometric understanding of the symmetries from the singular boundary homologies, let me just say a few more things about the compact models, and I have probably just 5 minutes, right? So in any case, I anticipated this will be an issue, but I can't help myself to highlight a few further consequences when we are dealing with the compact models. Because in this case, of singular compact models, we are including also now quantum gravity, and this global, including Haar-form symmetries, should either become genuinely non-anomalous gauge symmetries, or they should be broken. And we would like to ask ourselves what kind of gauge symmetries we can get now on these global models. And the story is quite well understood for elliptically fibered examples. Namely, those are examples that are due to F theory, okay, where we understand the origin of non-abelian gauge groups, really gauge ones, right, are associated with this compact divisors of AD Kodaira classification singularities that are in the elliptic fibration classified via ADA Kodaira classification. But we can also address the important issue of group topology as well in the compact cases from these approaches. And this is encoded in the arithmetic structure that the elliptic curve carries via Mordell Weil group. This arithmetic structure allows us to actually fix the group topology in terms of the Mordell Weil torsion, and specifying the actually global structure of now really gauge groups themselves. And so global structure is also gauged in this sense. And abelian gauge groups also have somewhat different origin. I haven't touched that in the non-compact case, but here we can handle it also because they are associated with the Mordell Weil free part. Namely, those are sections of elliptic fibrations, and Poincaré dualizing them will give us divisors of abelian gauge symmetries, and even more in the presence of non-abelian factors and abelian factors, we can actually employ the Shioda map of those abelian divisors by really identify the full global structure of the gauge symmetry, also in the presence of abelian factors. So this is really all encoded somewhere differently in the arithmetic structure of the elliptic curves. Okay. I can't help myself 1 minute that actually employing all these techniques, even down to 4 dimensions, we can do elliptically fibered fourfold with specific choice of elliptic fibrations that will lead us really 4-dimensional supersymmetric theory with quantum gravity that for particular elliptic fibration gives us this gauge symmetry of vertical and Mordell Weil divisors, and actually also the global structure is determined by using the corresponding Shioda map that is geometric. By choosing the compact 3-dimensional basis from the big class of Skarka-Kreutzer toric polytopes, using triangulation, we get a huge number of actually standard model constructions, adding fluxes. We get exactly 3 chiral families, and by choosing gauge divisors especially, we get gauge coupling unification. This is all wonderful, but the real hard work is to determine the exact matter spectrum, not just the chiral matter spectrum. That involves studying certain line bundles of corresponding meta curves. In this case, there are more involved bundles. Those are root bundles of restriction of anti-canonical divisors. And actually, you heard a talk by Martin Bies yesterday in parallel session on that, and slides on that are posted. This is just side advertisement that actually the study of elliptically fibered compact Calabi-Yau spaces has been really pushed quite far. Last minute, in our context, what we would really want to see, I was giving you this non-compact examples and associated the Haar-form symmetries there. How now in the compact examples, in particular in the case of elliptic fibration, this arithmetic structure of elliptic curve, namely Mordell Weil symmetry, connects to Haar-form symmetries that we found really from singular boundary homologies. Okay. So in this case, because we are in the global case, Haar-form symmetries that we'll have, even in this case, should be either gauged or broken. And this is general structure. How this is really happening is not so well understood. But 2 years ago, we did manage to really identify conditions under which such compact cases have anomaly-free gauge one-form symmetry. And that's precisely related, for example, to the torsion of Mordell Weil symmetry. So there's some physical arguments of gauge one-form symmetries in this case and how it relates then to this arithmetic structure. It turns out that actually non-anomalous gauge one-form symmetries, this condition is realized actually in all the known examples of a-dimensional n=1 supersymmetric string constructions. So when we focus on the global structure, we employed some refined study of string junctions and got all the a-dimensional constructions, the global group, and we saw is precisely related to specific gauging of non-anomalous one-form symmetry there in all these cases. Now, I don't have much more to say about really hands-on for other constructions of compact cases and how we would study the fate of this symmetries, in particular, this global Haar-form symmetries. We are approaching this problem by constructing really geometrically now compact example as the union of non-compact local models. And then once we glue that together into consistent compact case, the resulting CFT should now be a couple CFT of this associated with these components and includes gravity. In particular, we could now try in this approach also study relative cycles in each local components, glue them into global one and see what's the fate of those cycles. Some of these cycles, some of these defects become dynamical, namely they survive as compact ones, so they are gauged, and some are broken. And we expect to be able to study that more explicitly. I don't have much to tell you about that except the statements from elliptic fibration. But we are on the way to actually having all the compact constructions and the fate of this Haar-form symmetries for T4 orbifolds, and also working on some 6D orbifolds. Hopefully something to appear very soon. Thank you.
Hello, thanks Mirjam for finishing well in time. Questions? Yes, there's one.
Thank you for this very nice talk.
Thank you.
I had a question. In the non-compact case, you focused on 0-form and 1-form symmetries. Do you expect 2-form, 3-form, and so on symmetries?
Yes, we do. We do. But that would be probably for more complicated things. We have not gone into details of that.
But in this example, you think they're not present?
No, not in examples that have low enough dimension.
I see. It seems that if I understand the argument, it seems like the homotopy type of the boundary is essentially what you're computing with this 0-form and 1-form symmetries.
Right,
so
indeed.
It seems if you have a pi2 or a pi3 of the boundary, then
that would be associated with higher forms, right? I'm dealing primarily with pi1 here.
I see. So so essentially you're computing pi1
Right.
by this. Okay,
Right.
Thank
Indeed.
you.
Yeah.
Any further questions? Are there any questions over the Zoom? I had a quick question. If isn't anything immediately. So is there, did you mention a criterion when when the global symmetry would be gauged versus when it would be broken? Is there a some universal criterion? Or you have to look at it case by case?
We have to look really case by case. I have to say there is some hidden thing here you might have noticed when we did this more bottom-up approach. We really identified magnetic higher-form symmetry.
Okay.
Here, for the rest of our analysis, was really, we focused on electric ones. So when you compactify, what we see, the symmetries are broken. I'm telling you very preliminary things, okay, on that, right? But I know from those top-down constructions in 8 dimensions, right, all of them actually, that I can identify that with magnetic analog of one-form symmetry. So something to elaborate, work in progress that we hope to clarify in more details. And I couldn't say much in the compact cases. Thank you.
Okay, thank you. Oh, there's one more question.
Hi, Mirjam.
Hi.
Nice talk. Just like a quick comment on the gauging of the higher-form symmetries. I think we had a paper last year where we explicitly write down these conditions on how to gauge the two-form symmetries. And which sort of in the compact geometries and what conditions they have to satisfy, and it's like a sort of a generalization of the Mordell Weil torsion map.
Sorry, one-form symmetry.
Two-form symmetries.
Two forms.
Yeah, and we exactly in the follow-up we also precisely look at these orbifold bases of torus, mod, gamma, and so on, and where we also discuss those. Just as a comment.
Yeah, apologies for not mentioning your work on that, because it's not unrelated to some comments at the end of my talk.
Sure, thanks.
Okay, so let's thank Mirjam again.